작년 12월 구글이 윌로우라는 양자컴퓨터를 발표하면서 많은 사람들의 관심이 양자컴퓨터에 집중되었습니다. 0이 24개 붙은 시간 동안 현재 컴퓨터가 계산할 문제를 5분 만에 계산한다는 윌로우. 요즘은 과학의 발전이 너무 빨라서 이런 발표도 체감 자체가 안 될 정도인데요. 아무튼 구글의 발표 이후 또다시 양자 컴퓨팅 분야를 달아오르게 만드는 뉴스가 있었습니다. 이번에는 찬물을 끼얹었죠. 바로 젠슨 황의 발언이었습니다. 그는 고속바도를 달릴 것만 같았던 양자 컴퓨팅 분야가 사실은 20년 정도가 지나야 비로소 우리가 생각하는 상용화가 가능하다는 취지의 발언을 했습니다. 그로 인해 아이언큐 주가는 40% 가까이 폭락했죠. 이렇게 천국과 지옥을 왔다 갔다 하는 양자 컴퓨팅 분야는 아무래도 그 원리부터 어렵기도 하고 아직 우리가 체험도 제대로 못 해봤기 때문에 많은 사람들을 헷갈리게 만드는데요. 이런 양자 컴퓨팅 분야에 대한 궁금증을 조금이나마 풀어줬던 강연이 있었습니다. 연사로 세계적인 양자 컴퓨팅 분야의 석학 이토구의 게이오대 총장님과 김명식 런던 임페리얼칼리지 교수님이 좋은 말씀 전해주셨는데요. 이토구의 총장은 현재 일본 정부의 양자 기술 혁신 전문가 패널의 의장을 맡고 계시고 양자 물리학 분야에서 360편 이상의 학술지 논문을 발표하신 일본 양자 분야의 리더이십니다. 김명식 교수는 2010년부터 런던 임페리얼 칼리지에서 양자정보 과학 이론 분야 교수로 활동 중이십니다. 2016년부터 2019년까지 영국 국가 양자 테크놀로지 전략회의 멤버로 활동하셨으며 양자 연구에 대한 공헌으로 독일 훔볼트 재단의 지멘스상을 수상하셨습니다. 안녕하세요. 이번 강연은 게임 체인저를 꿈꾸는 양자 컴퓨터입니다.
Good morning, everyone. Welcome to today's panel discussion, Is Quantum the Next Big Thing? My name is Fabio Donati, and I'm Associate Professor of Physics at the IBS Center for Quantum Nanoscience at Iowa Women's University. So together, President Ito and Professor Kim will offer their insights on the current state of quantum computing technology, its future potential, and how we can cultivate talent and promote industries in preparation for the quantum era. With that, let's dive into the discussion and see if quantum truly is the next big thing. I would like to address the first question to Professor Kim. So we heard that quantum computing promises significant advances over classical computing in certain areas. So what are your expectations for quantum computers in terms of future performances and capabilities?
Thank you very much, Fabio, for your introduction and also giving me an opportunity to discuss about this vast question. Before I go into the capabilities of quantum computer, maybe the best is to explain what quantum computer is. Of course, I have very few minutes, so that it's an extremely difficult task to say anything about quantum computer in details. But in short, classical computer, which Fabio is mentioning, is a conventional computer, even supercomputer we have. And that uses billions of transistors. What does transistors do? That is a switch to allow electron to pass through or not to pass through, that kind of thing. So it's very simple switch. The combination of switches make the computation as we wish. On the other hand, quantum computer works extremely, very differently from the conventional computer using quantum theory. And now I said about electron. Electron is a particle, but in quantum physics, it is also a wave. So it has a duality between particle and wave, which makes computational tasks much faster. Why? Because of the parallelism it offers. But anyways, let's put it this way. Quantum computer has a potential to perform certain computational tasks much faster than the classical computer. Not all the tasks we have, but some of the tasks. And I can also say that there is a good opportunity for us to reformulate some of our very difficult questions or very difficult problems in computer to a form which quantum computer can solve faster.
Okay, thank you very much for the very nice answer. So with the next one, we can go a little bit further into the technology of quantum computing. So as you see here on the slide, we have examples of different companies investing in different technologies. So there's not yet a single platform that we are developing. So I wanted to address this question to President Ito. So from your perspective, is this diversity in quantum hardware beneficial? How does technology complement each other?
Thank you, Fabio. So there are so many different ways of building quantum computers. The far on the left, it's a superconducting qubit. It acts as if it's a single electron or single atom, so that it is quantum bit. Next example is a trapped ions. They're just trapping one atom at each position, and you can use each atom as a bit for quantum computing. And next example is a silicon quantum dots, utilizing today's silicon integrated circuit technologies. The other one is the topological qubits. This is very difficult to explain, but there's a physics called topological geometry physics that can actually lead to quantum computers. There is and diamond qubit is also interesting because you can introduce missing carbon from the diamond that actually act as a trap for one electron. So each electron trap at the diamond can be used as a quantum bit. And also neutral atoms is just, you can make arrays of single atoms and so on and so on. I attended the very first conference on solid state quantum computing in 2003, already 11 years ago. Back then, it was all about superconducting qubits. But now, optical qubit is missing from here. Optical qubit is very big. It's a QERA is one company. Superconducting qubit, IBM, Google, Rigetti are the leading companies. Ions, IonQ, Quantinium, and so on. Silicon, Intel's working on it. So which one wins is the question. Which one wins is appropriate. My answer is no, because each quantum bit has pros and cons. So it's going to be hybrid in the future. Probably optical qubit will be working together with superconducting qubit, or possibly with silicon qubit. Ion qubit must work with optical qubit as well. And when it comes to hybrid computing between quantum and classical, maybe silicon has an advantage.
Thanks a lot for the great explanation of the different platforms. So we are all dreaming about the new technology, but the question we may address now is, where are we now? So this is what you can see, what a typical schematics of the quantum computing eras that is defined by now. So as you see, we are kind of in the middle of the progress. So after the theoretical and experimental era, now we are in what we call the noisy intermediate scale quantum era. So basically, in this phase, we are still developing the quantum computer. We already went through the theoretical and experimental part, but quantum computers are still under development. So I want to address this question to Professor Kim. So what can we realistically do with quantum computers now? And what should people be aware of in terms of current capabilities?
Thank you. So there was a Nature article a few months ago, asking exactly the same question. What can we do with the current status of quantum computer? And the answer there was absolutely nothing. That was the answer, because it is the error rate of each. So to perform a computation, you need to have gate operation, let's say, 1,000,000 times, or even billion times. For each gate operation, if there is 0.1% error, then it accumulates, and at the end, you get random answer. So that's the thing what Nature article said. That was quite disappointing, very disappointing. However, as you can see in the next slide, cloud services you can have. IBM provides cloud service, and also the other companies, through which those services can be very useful to train yourself and also to train the people in your own company or in your own university. Last year, the UK government published National Strategy in Quantum Technology. One of the important missions in that strategy is to increase the awareness public awareness and company awareness of potential quantum advantages from currently 25%. So what I mean is that only 25% of the relevant industry members are aware of the advantages. They want to increase that percentage into 75%. At least each company has a kind of the section on developing quantum algorithms and making use of quantum advantages. So current status, I think that even though I said absolutely nothing, not really nothing, it's but all the debatable, the results we have, and we don't see the real quantum advantages for the real problem we have, but still there are very good opportunities to increase that as the hardware gets better.
Thank you very much. So I think this also opens the ground for the next question, because we get more specifically into how we can use a quantum computer to solve problems. As we heard, it's by now very hard to big problems yet, but we are developing software for that, right? So we are developing software that goes together with the hardware. And that, in this sense, I think I wanted to ask you, President Ito, what are the problems that we are mostly trying to tackle with quantum logic, and what are the most promising areas where we can find the problem that we can solve with quantum computing?
Okay, thank you, Fabio. At Keio University, where I work, we started working very closely together with US IBM in 2018, 6 years ago. 6 years ago, we had this opportunity to use IBM quantum computer for the first time. But when we actually tried to use it, we could not perform even one logic gate, zero calculation whatsoever 6 years ago. But then, only within 2 months, IBM developed a new quantum computer chip that allowed us to perform 2-qubit operations. And then, within the next 2 months, we were able to perform 3-qubit operations. So where are we now? The quantum computer is like first-year elementary school student. Last year, the quantum computer graduated from kindergarten. But when you actually go to kindergarten's sports day, of course, these kids cannot run as well as adult grown-up. Why are you so happy to see those kids? They have the future. So working closely with IBM, we have been educating their IBM machines by developing algorithms and software. So we think that within 10 or even 5 years, we think we will be able to create some kind of a useful output with a quantum computer. Chemical engineering companies are also interested in working together with us because simulation of a molecule is a very difficult task with today's computer. If you add one atom, then calculation time doubles approximately. So big atoms is impossible to be simulated by today's computer. But quantum computer basically should be able to perform such calculation because molecule is a quantum item, so anything quantum should be able to be simulated with quantum computers much better than your computer, classical computer. So in this example, we are studying different molecules for OLED, optical light emitting diode, and in this particular case, we are replacing some of the hydrogen with deuterium, heavier hydrogen. Then we will try to find out by which replacement we can get better luminescence, more light coming from each molecule using quantum computer.
Thanks for the clarification. Actually, I would like to stay a little bit longer on the topic of the software, and actually I wanted to touch a point that also connects with other sessions today. So there's speculation that artificial intelligence and quantum computing could work together. So then I address this question to Professor Kim. Do you think that AI can help accelerate the development of quantum algorithms? or is it just a theoretical speculation?
Okay. So the question is, can AI be able to build a quantum computer? That's a
Yes.
question. I think in a way, yes, because we need lots of control. Quantum computer is a series of controlling atom, photon, also superconductor interaction, and silicon as well. So to control those things, we need very good controlling pulses. And to find the right controlling sequence and right controlling pulse shape, the AI can help. Then how about this, the other way around? Can quantum computer help AI or machine learning? I can say two things. One is that machine learning uses lots of matrix calculations. And quantum computer uses, so they decompose all the matrix calculations into a smaller form and then does the calculation at the same time. So there is a good potential for quantum computer work with AI to make sure that we can perform the machine learning faster with a smaller number of data sets. There is a speculation. We don't know yet, but it's a quite plausible assumption that we'll be able to do that. And another thing is that one of the problems in machine learning is energy consumption. A lot of energy it will consume. More than half of the electricity we generate will be on computing in a few years' time. Can we sustain that? I think probably not. Then what we have to do is we have to find a good way to compute those things, saving energy. And what can we do? One solution is to find a good material which requires less energy to perform the same computational task. And quantum computer may be able to help in finding the right material.
So the next topic I want to address is the relation between quantum computing and society. So maybe I will go to the next slide. And then as you see from this slide, there's numbers of how many graduate people we have per year in quantum technology and related fields. So definitely to unlock the potential of quantum computing, we need highly skilled workforce. So the question I want to address to Professor Kim is, are current efforts in education and talent development enough to prepare the quantum era, or should we be do more about that?
I think we need more. Especially Korea needs more workforce in quantum area. In the UK, so we started about 25 years ago to have a special cohort of quantum PhDs. Now they have been investing in quantum computing education for more than 25 years. And they have now generated lots of PhDs in quantum. But is that enough? No, not to cover the whole industry of quantum, no. But you may say this, by the way, you always said possibility. So far you said possibility. There is a good potential to deliver quantum advantages over the classical machine. Do we need to spend such a large amount of money, the government money or the public money or the private money on quantum while it is only possibility? Yes, because it gives an opportunity for us to be able to control the materials at the very smallest level. They say about 1 nanotechnology, 3 nanotechnology, 1.5 nanotechnology. 1 nano means about 5 to 10 atoms. If you go down that level, quantum mechanics is becoming much more important. Instead of avoiding the quantum effects because we don't know how to control it, let's use it. And those workforce will be able to know how to use it. So there is a good possibility.
So then let me ask you, maybe to both of you, a final question about an important point, which is about the funding. So let me show you a couple of slides about that. So one is the global investment in quantum technology provided by the countries all over the world. So you see you can have a total estimate of about $40 billion in 2023. Now, let's also have a look not only on the government investment, but also to the private investment. And you see this is also getting significant. We get about $2 billion in 2022. Of course, the private sector is more fluctuating. You see ups and downs in the story, but the long trend is definitely increasing. So now I want to ask a question, maybe first to President Ito, and then if Professor Kim wants to add up something. How do you expect this future landscape will look like?
Originally, it was only the government governments of different countries who were supporting the quantum computing research. But now, as you saw, so many companies are seriously putting their own efforts and also resources into quantum computers. IBM, as I said, we have been working very closely with them. It's amazing how much money and people and everything they put into this field. So that itself tells you that, at least IBM's betting on this. So this must be something of the importance. Government level, what's important is fundamental research that goes along with this industrial effort. Quantum physics always finds something new so that can be directly and swiftly implemented on the industrial development. So this parallel effort between basic research and industrial development is very important. So this balance must be taken very seriously. In the United States, there are companies and also government working very nicely together. In Japan, I'm in charge of quantum policy panel, so I know how much we are spending and so on. But we are still having trouble convincing industries especially industries in the hardware arena, to convince them to come into this field. I don't know the situation in Korea, but probably government is a dominant source of the funder. So we'll see whether Korea or Japan or other countries can catch up with US or some parts in Europe, just like you did very well in silicon semiconductor industry. So whether we can come afterwards to catch up is a big question. What do you think, President Kim?
Yeah, as Professor Ito mentioned, the funding to the research has not, the government funding, the public funding has been enormous. As you can see, that the funding is growing, and now UK has their own national strategy, Germany has their own national strategy, Japan has their national strategy, and China is spending a huge amount of money. At Imperial, there are quite a few Chinese students, and the most popular topic for them is probably quantum computing. And now UK government is not very much interested in supporting physics only. They say that it's not fundamental science anymore. You have to include engineers. You have to include the business school. Otherwise, you will just generate your clones, your own copies to stay in academia. That's not what we want to see in quantum tech. And next year, the UNESCO decided to have next year as the International Year of Quantum Science and Technology. They didn't forget to have technology. And in fact, technology is probably the bigger scale. So that's an important fact. And also, as Professor Ito mentioned, industry interest will be important, not only from the existing companies, but also startups.
Thank you very much for this overview on the funding and the possibility for companies. With this, I want to thank our panelists first, and of course you for your attention, and let's remain hopeful that we will have exciting development to come very soon. Thank you very much.